Okay, these are the solutions of some homework problems that I asked. So, number 2, calculate the power of an engine that can accelerate a ship of mass, given us that tons from rest to a speed of 30 km per hour in a time of 5.5 hours. Now, to calculate power in watts, we need mass in kilograms, speed in meters per second, and time in seconds. So let's start with converting time to seconds. We have to multiply by 60 to get to minutes and then 60 to get to seconds. So we end up multiplying by 3,600, which gives us 19,800 seconds. That's our time. To change this mass to kilograms, I'm going to write this as 10 to the power of 8 kilograms, as 1 ton is 1,000 kilograms. And to convert speed from kilometer per hour to meters per second, I'm going to divide this by 3.6, as I explained earlier in class, which gives me 8.3 meters per second. So to calculate power, we know we have to find the work done in unit time. So whenever you're calculating power, we do have the time. We ask ourselves, what kind of work are we doing? In this case, an engine is accelerating a ship, so kinetic energy is being produced. So the work done is the change in kinetic energy from rest. So initial is 0 and final will be the kinetic energy with these terms. So basically I'm going to do 1/2 mass in kilograms times the velocity in meters per second squared, because kinetic energy is 1/2 mv squared. I divide that by time, because power is work done divided by time. So I have to decide what kind of work is being done, the change in energy in the context of the question, and divide that by time, which in this case is that number. When you substitute all those numbers, you get your answer to be 2.1 times 10 to the power of 5 watts. I also asked you to look at part D. A boy of mass 56 kilograms who can climb 100 steps each of 20 centimeters high in 18 seconds. Again, we're looking for power and we want to know the work done divided by time. We know the time, what kind of work is being done. In this case, there's a mass that is climbing a certain height. So I know potential energy is changing. So I'm going to do mgh divided by the time. So I have the boy's mass, 56 kilograms, and I'm going to use 9.8 for g. And the total height the boy climbs in meters is going to be 100 steps, each of which is 0.2 meters. This is 20 centimeters, which means 0.2 meters. So this is the total height the boy climbs in 18 seconds. This gives me 610.4 watts. Okay, the next question was number 4. We have a drag racing car. We have its mass. It goes from rest to a speed of 120 meters per second in 6 seconds. Take a minute to think how fast that change is. That is a huge amount of acceleration. Well, we're talking about a drag racing car and we're looking for its efficiency. But the question takes us step by step. The goal is to calculate the percentage efficiency. Now, let's define percent efficiency first. We define percentage efficiency by 100 to make it percentage times useful over the input. This could be useful power divided by the input power. Alternatively, you could use useful work done divided by the input energy. This question walks us through using the power. So calculate the power released by the fuel burning in the engine. We have 28 kilograms of fuel, and each kilogram of fuel provides 55 megajoules of energy. And it's doing this in 6 seconds. So we can find the power released by the fuel by looking at the fuel quantities. We want the energy from the fuel in this time, which is given as 6 seconds. So I know I'm using 28 kilograms of fuel, and each kilogram produces 55 megajoules of energy. And this is happening in 6 seconds. So that's my math. I get 257 times 10 to the power of 6 watts. Now I'm looking for the final kinetic energy of the car. Well, kinetic energy is calculated 1/2 mv squared. So I'm just going to substitute my numbers. I have the mass and I know the final speed it reaches to. When you calculate that, you get 3744 kilojoules. Now, the useful power of the car is the useful work. So the ultimate work done on the car, which is the change in kinetic energy. So I'm going to take that value. Okay, let me correct that, sorry. I'm going to take that value and divide it by the time I do this work in, which is going to give me 624 kilowatts. So what do I have here? I have the useful power and I have the input power. So now I can go and calculate this ratio. I'm going to do 100 times the useful power, which I found above, divided by the input power, which is 257 is 10 to the power of 6. When you calculate this, you end up with 0.24%, which is extremely low. Well, imagine a drag racing car doing this work. You're going to hear a lot of sound and there will be a lot of heating in the tires. So there's a lot of energy transferred to the surroundings doing this work. So that's efficiency. Now let's talk about question number 7. Okay, in question number 7, we are given a track. In this track, we have a starting point at point A. There's no friction given. So the roller coaster, the cart moves along the roller coaster. We are going to use energy conservation here because we know the initial speed and the initial height. So the whole idea is total energy, which is potential plus kinetic at any point is going to be constant, which means if I calculate the potential energy at A and the kinetic energy at A, that's going to be the sum of potential and kinetic at B. So let's calculate this total energy first. We want to find the truck's speed at B. So what do I know? I know the mass, which is 400 kilograms. And at A, the speed is this, and we know the height at A, which would be 35 meters. And the height at B is given as 5 meters. So what I'm going to do is write a full equation of before and after at point A and at point B. So what is the potential energy at A? Mass, I know, is 400. So I'm doing mgh at A. Mass is 400, G is 9.8, and height at A is 35. So this is the potential energy at A. I'm going to add the kinetic energy at A, which is 1/2 mass times the speed at A squared. So this is going to give me the total energy, which actually calculates to 138,000 joules. Now this is equal to the same at B. So if I know no energy is lost to friction, I know now the mgh at B, so I'm using 5 as the height, is going to be equal to 1/2 m VB squared. So that's going to be equal to 19600 plus 200 VB squared, and that calculation is going to give me VB to be roughly 24 meters per second. Now in point D, we will really do the same thing, but D is at ground level, so height equals 0, which means all of this total energy is going to be kinetic energy. This is the total energy we calculated from part A. It's constant anywhere during the motion. So I can simply write 138,000 joules is going to be equal to the potential energy at D, which is 0, plus kinetic energy at D, which is that. And that's going to give me 26 meters per second. Part C is asking for the truck speed at E. At E, I know that the height is 20. So again, I'm going to use the total energy, 138,000. This is now going to be equal to the potential energy at E, which is not 0. So I'm simply going to calculate. I know the mass. I know the G. I know at E the height is 20 plus 1/2 mv squared at E, which is going to give me VE to be about 17 meters per second. Alright, let's move on to question 8, which looks very similar but with friction. So we know there's a constant friction force acting on the car throughout the whole track to be 750 newtons. Let's start with conservation of energy again. At point O, it starts from rest, so there is no kinetic energy at O. So the total energy will be the potential energy at O, which is mgh, which is given as 62 meters. Now, this is going to give me 729,120. This is the potential energy at O, which is the total energy because kinetic is 0. So I know this is my starting budget. This is my starting total energy. What I'm going to do, if the question was similar to the one before with no energy lost, we would set this equal to mgh at P plus 1/2 mv squared at P, which we will do, but now we have friction. So what I have to do is total energy minus the work done by friction, because that's what friction does. It steals energy. That's going to be equal to the potential energy at P plus the kinetic energy at P. How am I going to write that? Now I know this number. This is 729,120. We know that the definition of work is force times the displacement. Well, I know the force of 750 acts for a distance of 420 meters from O to P. So this track is 420 meters. So that value is going to be subtracted from total energy, lost to friction, not useful anymore, which is the remaining energy at P, which I can write as mass mgh. I'm doing potential energy. I know the height is 35. And that remaining will be kinetic energy. And when I solve for P, I'm going to find about 2.0 meters per second. If you use 9.81, the answer is going to calculate to be 2.2. The last part, calculate the total distance that the car will travel after it's passed the point P. Well, for this, I need the total energy at P. So this value, the energy at P, is going to be the work done against friction after that point. So to calculate that value, this minus this, gives me 414,120. I'm going to set that equal to, well, this is going to be the work done against friction, which is going to be the force of friction times the distance after that point. So that's 750 times S after that point, which calculates to the answer, which is about 552